Okay, so where does polarity come up? Like, like it comes up later in the unit, and we are going to have a lab over it. But a good thing to remember is just that if something dissolves in something else, so you have a liquid and you can dissolve something in that liquid, then whatever you dissolved is like the liquid that dissolved it. And so polar things dissolve in polar things, and nonpolar things dissolve in nonpolar things. And then there's kind of a scale where it's not as black and white as that, where you kind of like have, like on one scale, like we might have polar over here, and on the other side, we might have nonpolar. So like this is polar and this is not polar. And then there's like variations of it. So like it's kind of polar or it's kind of non-polar. It's dead in the middle, and so you kind of see different variations. And we'll kind of look at that in our lab this unit, where I give you different solutions and I have you separate something real simple, a little dye, and then you have to use that information to figure out what dyes did I mix up. So it's a pretty good experiment when we look at the concept of polar versus non-polar. So this will come up again on the lab. So, all right. And it's a lab we can do even, it's a lab we'll be able to do. It is something I am planning to do. All right. This is just a specific thing, ionic character. They always ask about this. And um, there's a definition here, but it's hard because I hate giving the very specifics on this because again, there's there's levels of ionic character, and so the more the this is again a place where I can give you a definition, but not everything is going to hold up. So what the heck is ionic character? Well, you have something called electronegativity, and you have this chart. This is in the data booklet, so you always have access to this, so you never have to memorize this. This is in the data book. And what does electronegativity tell us? Well, it's going to tell us whether or not chemicals want electrons. Read this. I look at this and I say to myself, okay, the bigger the number, the more something wants electrons. Okay, so take a look at fluorine. It has a 4.0. That's the biggest number on here. Fluorine wants electrons more than any other chemical on the entire periodic table. All right, now if you look at something like sodium, 0.9, it doesn't really want electrons at all. We talked about it, right? Like it wants to become Na plus 1, which means that it doesn't want to get electrons. So it's a low number. So the low numbers don't want electrons, and the big numbers want electrons. But the scale only goes to 4. So you have a fairly small scale. But if you look at two chemicals, let's say calcium and oxygen, if you have a pretty big difference, so calcium is 1.0 and then oxygen is 3.4. If you have a pretty big difference, and so the difference here is 2.4, the bigger the difference, the more ionic the bond is. So a big difference is very ionic. The smaller the difference, the less ionic the bond is. And then if you have a very small difference, it's not ionic at all. It's probably covalent. So if we put sulfur and oxygen together, you have 2.6 and you have 3.4. All right. Well, that's only going to be a difference of zero point 0.8. Well, that's a very, very small difference, and so that's not ionic. Well, something like sulfur dioxide, SO2, that's a covalent bond. And so as the number gets smaller, It's more likely to be covalent when you stick chemicals together, as the number difference, not the number difference, as it gets bigger, more ionic, smaller, more covalent. Now, let's look at the chart and let's think about something. There's some chemicals missing. And what are those chemicals? Well, what about those chemicals? They're supposed to be like right here. What the heck are those? Well, those are our noble gases. Why are they missing? They're missing because they have values of 0. They don't have electronegativity values because they have no interest in bonding. They have no interest in doing anything, so they're just sort of missing. And so that's something to kind of note from the table. Okay, so then we get this thing called ionic character. Ionic character is just like how ionic is a thing. So ionic character, what does that mean? That is how ionic a thing is. Is it likely to be like salt or not? Is it likely to have a high melting point? Is it likely to dissolve in water? So an electronegativity difference of 1.8 or more is guaranteed to be an ionic bond. Now, are there things that are going to be close that we call ionic? Yes. But if you hit what IB is saying, if you hit that 1.8 or bigger, that's a guaranteed ionic bond, right? Now you have this chart. So here's how the question will look. It'll say, which of these is the most ionic? Which of these has the most ionic character? We'll just look for the one with the biggest difference in the two chemicals, right? And then this next chart right here, once again, it says that the pairs of elements that react most easily to form ionic compounds are metals on the bottom left and nonmetals on the top right. So this is from your textbook that we don't really use a lot, but that's what this is from. It's saying, hey, chemicals from down here, francium, combined with chemicals from up here, fluorine, are most ionic. Well, that makes sense because the number differential there is 3.3. That's about as big as you can possibly get. As you start to add chemicals together that are closer together, then you start to see that you're not going to make ionic compounds. So that's just what that is. Ionic character is pretty easy. Okay, that's kind of the end of ionic. What I really want you to take away from ionic is you need to be able to like recognize if you have a some trait given to you. Like let's say they tell you that you have a chemical and you've got this chemical and they give you some clues, right? They're like, it's a solid and it conducts electricity when you dissolve it in water. And it has a melting point of 3, and let's change that. Let's go 560 degrees Celsius. Okay, so you got these traits. Well, solid doesn't help you. Conducts electricity if you dissolve it in water, that does help us because only ionic does that. Melting point of 560, not a guarantee. So a lot of times you see stuff that like these are not guarantees because they could be metals. This is a guarantee because metals do not dissolve in water. The only thing that dissolves in water and conducts electricity is ionic. So that's something that you want to be able to do with this. And just understand the ionics, kind of how they form, etc. So on our next bit of notes, we're going into covalent bonding. So now we're no longer doing metal, non-metal. These are all non-metals. We're going to do dot structures. We're going to do shapes. We spend a lot of the unit here. And so you can see, oh, there's some dot structures. There's some various shapes and structures. And so we're going to look at that next, but we're going to start that on the next set of notes because that's going to get